Here shows the map of Romania.
We've looked at the state space of cities in Romania, a two-dimensional physical space. But the technology for problem solving through search can deal with many types of state spaces, dealing with abstract properties, not just XY position in a plane. Here I introduce another state space, the vacuum world. It's a very simple world in which there are only two positions as opposed to the many positions in the Romania state space, but there are additional properties to deal with as well. So the robot vacuum cleaner can be in either of the two conditions, but as well as that, each of the positions can either have dirt in it or not have dirt in it. And now the question is, to represent this as a state space, how many states do we need? The number of states can fill in this box here.
The title is Other State Spaces. The figure shows two squares side by side. Square A is on the left, and the vacuum robot and the dirt are in square A. Square B is on the right. The dirt is in square B. Now, please answer the number of states.
And the answer is there are 8 states. There are 2 physical states that the robot vacuum cleaner can be in, either in state A or in state B. But in addition to that, there are states about how the world is, as well as where the robot is in the world. So, state A can be dirty or not. That's 2 possibilities. And B can be dirty or not. That's 2 more possibilities. When we multiply those together, we get 8 possible states.
The number of states is 8, computed from 2 times 2 times 2.
Here's a diagram of the state space for the vacuum world. Note that there are 8 states, and we have the actions connecting the states, just as we did in the Romanian problem. Now let's look at a path through this state. Let's say we start out in this position, and then we apply the action of moving right. Then we end up in a position where the state of the world looks the same, except the robot has moved from position A to position B. Now, if we apply the action, turn on the sucking action, then we end up in a state where the robot is in the same position, but that position is no longer dirty.
This figure shows all 8 states of the vacuum robot problem. The first state is the robot is in square A. Square A is dirty and square B is dirty. The second state is the robot is in square B. Square A is dirty and square B is dirty. So, move from the first state to the second state, the robot should take the move right action. The third state is the robot is in square B and square A is dirty. So, to change from the second state to the third state, the robot should take the clean action.
Let's take this very simple vacuum world and make a slightly more complicated one. First, we'll say that the robot has a power switch, which can be in one of 3 conditions: on, off, or sleep. Next, we'll say that the robot has a dirt-sensing camera, and that camera can either be on or off. Third, this is the deluxe model of robot, in which the brushes that clean up the dust can be set at one of 5 different heights to be appropriate for whatever level of carpeting you have. And finally, rather than just having the 2 positions, we'll extend that out and have 10 positions. And now the question is, how many states in this state space?
The first line is power, which can be on, off, or sleep. The second line is camera, which can be on or off. The third line is brush height, which can be 1, 2, 3, 4, or 5. The fourth line is the number of positions, which is 10. Now, please answer the number of states.
The answer is that the number of states is the cross product of the numbers of all the variables. since they're each independent and any combination can occur. So for the power, we have 3 possible positions. The camera has 2. The brush height has 5. The dirt has 2 for each of the 10 positions. So that's 2 to the 10th, or 1024. And then the robot's position can be any of those 10 positions as well. And that works out to 307,200 states in the state space. And notice how a fairly trivial problem, we're only modeling a few variables and only 10 positions, works out to a large number of state space. And that's why we need efficient algorithms for searching through state spaces.
The number of states is 307,200. It is computed from 3 times 2 times 5 times 2 to the 10th times 10.